Hello, in today's video we're going to be talking about valence bond theory. Now we already know that if we draw the Lewis dot structures of certain molecules, we can predict what the bond angles are going to be through that AXE notation. This is another jump in the thought process of what a bond is and how it forms in a molecule. So valence bond theory tells us that a bond only forms if you have an overlap of orbitals. So we know what these orbitals look like. An s orbital is a sphere, a p orbital is a dumbbell. Okay. And we have three different p orbitals. We have this one, we have this one, and we have the slightly bent one, that one. So we have three different p orbitals. Now valence bond theory tells us that if we overlap any of these orbitals, these p orbitals with an s orbital, we will get a bond forming there. So let's try that. Let's try to bond the s orbital with the p orbital. If we bring these closer together, what we end up getting is a dumbbell that is overlapping with the s orbital, sp. This would be considered a bond in valence bond theory. So this is a bond. Let's try and overlap this s with this p orbital. We have their s, we have our p. There is very little overlap in the way that this p orbital is aligned compared to the s orbital, sp. So this does not create a bond. I'm going to write bond and I'm going to scratch it out. So all valence bond theory does is it says if we want to create a bond within a molecule, we have to have a certain overlap of the orbitals that are involved. And that's what we see here. An s can overlap with a p. A p can overlap with a p. Things of that nature. So anytime you have this overlap, you get a bond. Now there is one downfall to valence bond theory. It does not predict the bond angles that we are expecting to find in certain molecules. So this is the idea, the understanding behind valence bond theory. The more overlap you get, so if we had an extremely large overlap, the stronger the bond. If there is no overlap, you're not going to create a bond between those orbitals. So we also know that valence bond theory does not predict correctly what the bond angles are between certain molecules. So let's take a look at the BF3 Lewis dot structure and predict what those bond angles are going to be of that molecule. We know that boron is one of those special elements on the periodic table that only need 6 electrons in its valence or 6 electrons surrounding it to be satisfied, to satisfy its octet rule. So we can draw the Lewis dot structure to look like this. Lots of dots. And we know that the bond angle between the two fluorines is going to be 120 degrees. Now, valence bond theory, bonding a p with a p, overlapping a p orbital with a p orbital, or a p orbital with an s orbital, there is no possible way to get out 120 degrees, just based on simple geometry. So what we've come up with is a way of combining certain orbitals in such a way that we predict we end up getting out these bond angles. And those are known as hybridized orbitals. So let's take a look at how we hybridize orbitals. And you're not going to have to be hybridizing orbitals on the exam or the final. However, I want you to be aware of how it's done. In your case, you will have to be able to identify what the hybridized orbital is based on the Lewis dot structure. But here I'm going to show you how we actually create these hybridized orbitals. So if we have a 2s and we have 3 2p's, we know that if we were to overlap this p with this s, we're not going to get the 120 bond angle. So what we can do is we can combine the s and the p orbitals. And there are certain ways that we can combine this, and there are certain rules that we have to abide by. So if I were to combine the first s orbital, or the 2s orbital, with the first 2p orbital, I would end up getting 2 hybridized orbitals. So the first rule is the total number of orbitals that you combine, that you hybridize, has to equal the number of hybridized orbitals. So here we had 1, 2. So we're going to get a total of 2, that's a horrible square, 2 hybridized orbitals. And we're going to name these a very simple name. We're going to get an s, and we combined it with 1p, So these two, they're degenerate in energy, they are called an sp hybridized orbital. They have the same energy, and we can place our electrons just like we would with every other type of orbital diagram. So what ends up happening is these two sp hybridized orbitals replace our s and our p, and we end up getting an orbital diagram that looks like this. Well, this hybridizing one s and one p still does not give us 120. This would end up giving us 180. That's great. But if we go back to our original one, 2s, here's our 2p, and now we hybridize 3 regular orbitals. So we hybridize these 3 regular orbitals. We end up getting 3 degenerate or hybridized orbitals. So the total number of hybridized orbitals you get out is equal to the number of orbitals that you put in. And we have a very simple way of naming these ones. It's an s, there's 1 p, and then since there are 2 p's that are being hybridized, we place a 2 superscript. So now, out of 3 orbitals, we end up getting 3 hybridized sp2 orbitals. And again, those sp2 hybridized orbitals replace our original orbitals. We still have our 2p. And now what we end up getting is an orbital diagram that looks like this. sp2, 3 sp2 hybridized orbitals, 1 2p that has not been hybridized. And if we were to look at the bond angles between these sp2s, we're going to end up with 120 degrees. So this hybridized orbital theory came out, the hybridizing orbitals came out of valence bond theory so that we can predict correctly these bond angles we see experimentally. And that's what happens a lot of times in chemistry. We have experimental evidence that shows one thing. Our theory doesn't really predict a certain aspect of experimental evidence, so we go back through and we manipulate our theory in order to follow along with what's seen experimentally. And this is all of our valence bond theory, all of our hybridized orbitals bonded into one video. Now, in class, I'll teach you how to write out and how to identify which hybridized orbital you are in. And all you have to do is really count the total number of bonding groups surrounding the central atom. We would say an sp2 hybridized orbital. So we're going to do a lot of practice problems like these. What I just did there, sp2 hybridized orbital, that is the extent of the hybridization that you need to know. I'm not going to have you hybridizing orbitals. I just want you to be able to identify what they are based on the Lewis dot structures. So with that, I want to say have a great night. I will see you all in class tomorrow. And don't worry, we'll do a lot of examples in class tomorrow. So I know this is kind of confusing, but we'll break it down tomorrow. Have a good night.